consideration of this question. We've got the top plate and the bottom plate, like so. So as a capacitor goes, we know that whatever the area is here, there's area there, there's going to be charge on that plate. The charge density is going to be Q over A. Just jotting down a few things that I saw when I was looking over there at what question F is about. They're going to put this a conducting plate in here. And it's important to be clear about this. The conductor is not going to be an insulator, or is not a dielectric. A dielectric is, I probably spelled conductor wrong. A dielectric is an insulator by nature so that it can't pass charges. If you filled the gap between two metal plates of a capacitor with a conducting material, it would merely conduct the charge from one plate to the other. So a conductor doesn't act as a capacitor. In fact, what the conductor is going to do is the conductor effectively, if this is the positive plate and this is the negative plate, the conductor is going to effectively reduce the distance between the plates. It does so because the charges in the conductor are going to align themselves in such a way to match perfectly the charges that exist on the two plates of the capacitor and separate out that amount of charge on the surface of the conductor, so that inside the conductor I'll have positive Q here. I'm sorry, not positive Q. I'll have negative Q here and positive Q here, perfectly lining up with the negative Q of the capacitor and the positive Q of the capacitor. So what this effectively does is take what was the original separation distance and create two smaller capacitors that have smaller separation distances and places them in series. Meaning what we have here with this slab of metal in between the two plates wouldn't be any different than if I took this conductor and all this out and merely made two smaller capacitors and connect them by wire, like so. So that this was capacitor 1 and this is capacitor 2, and they were in series, as so. So generally, since we say that the capacitance is kind of a ratio of the surface area to the separation distance, what we effectively do by placing this metal slab in between the plates of the capacitor is we make the separation distance ultimately less, but create two different capacitors. So how that affects our answer might be a little bit more ambiguous. So going back to the problem, as the charge divided by the potential difference. That's how we define a capacitor. And this particular capacitor has been established with a charge density already on it. And we are placing for lack of a better word, X for thickness. And this is D. The area of the plates is not changing. The potential difference was connected to the plates and then taken away. So that means that the charge on the plates cannot change. If the area of the plates doesn't change and the charge doesn't change, that means anything I put in blue here has to be a constant. Right now, that's the only thing that has to be a constant is the amount of charge on the plates. This is a parallel plate capacitor. And because it's a parallel plate capacitor, we know this capacitance is, its capacitance is also equal to epsilon naught A over D. Now, they put the slab in the middle and, effectively making two capacitors. I'm not convinced that it would make any difference if we just move this to here and made that our new capacitor. You follow me? And we can leave it in the center. It just makes more work for us in considering what they want us to do with that best fit line. But if we put it over here, then what we really have is a new gap between the plates. That's D minus X, where X represents the thickness of the plates. Now, if you don't want to do it that way, then that's fine. The other way to do it is to consider leaving it like this. We're assuming the slab is put right in the middle, and this is going to be, say, X1, and this will be X2. Those have to be the same thickness, I guess. Let's not do X and X1. Let's do, I need a term here, so I do not make this too confusing, but how about, for just this moment, I need a letter. I'm going to go with Y. They have to be the same there. And so Y is going to be D minus X over 2, because it has to be half that gap. Does that make sense so far? You might not understand why I'm doing this, but I have a goal. So the new capacitance, it's going to be two capacitors that are in series. So I should write this as, because series is the sum of the inverses, Y over epsilon naught A plus Y over epsilon naught A, where I've taken the definition of capacitance and inverted it based on the new size. But this is Y. It's D minus X over 2. So I can put this as D minus X over 2 epsilon A plus D minus X over 2 epsilon A. Which will equal 2D minus X over 2 epsilon A. And I get D minus X over over epsilon A, which equals my 1 over my new capacitance. Kind of out of space here, but I'm doing that real fast just to kind of prove that the new capacitance is still epsilon naught A over D minus X. So basically, that slab of metal just reduces the separation between the plates. Is that okay, Jake? All right, so let's pull this all together now. And I've got Q over delta V equals epsilon naught A over D minus X. Q doesn't change, A doesn't change, epsilon doesn't change, D doesn't change. They're making X bigger and plotting delta V. So delta V is on the y-axis, so I'm going to invert this All I'm trying to do is kind of get my linearization information. So I'm going to say delta V equals Q over epsilon naught A times D minus Q over epsilon naught A times X. This is all a constant. We plotted this versus this. So I'm expecting a line with a negative slope, and this will be the result of the slope of that line. Now, they wanted me to find two things. And at this point, it's been a long time. They want me to find the distance between the capacitor plates and the charge density on the capacitor plates. All right. Well, I can use the slope to figure out the charge density, since it's going to be minus Q over epsilon naught A, and this is the charge density. And if I want the separation of the plates, looks like it's all bound up with the y-intercept. So back to here, get the y-intercept. That's pretty close to 25. And once you've got the y-intercept, you get the slope too. It looks like the slope drops down 5 for every 2 centimeters. So I'm looking at negative 5 over 2 volts per centimeter, and y-intercept 25 volts. So I'm just pulling that right off the graph real quick. So I think all you're going to be doing is taking these values off the graph and then making your comparisons there. That should give you more than just a starting point. It was kind of fast and rushed. Does that give you some place to go, Jake? Okay. Now, I want us to be thinking about our crib sheet, our cheat sheet, the piece of material that we get to have in front of us during this exam. We only have 3 basic areas that our exam covers. We have electrostatics, capacitance, and DC circuits. Those are the 3 basic places that are within our curriculum. And I know that you might wonder why I broke it up this way, but the flow of charges often is pretty different from the electrostatic sides, and capacitance tends to be in the middle. It tends to bridge that because we can have, RC circuits, which bridges these things together. Electrostatics, we know, is point charge, charge distributions, and ultimately it leads to, or is evaluated with Coulomb's law, Gauss's law, and we tend to develop force, electric field, and electric potential. So when we see point charges, we tend to think that there's going to be some question requiring us to use Coulomb's law or Gauss's law that's going to eventually ask us about the electric field or the electric potential. We need to recognize that positive potentials have certain effects on the system and negative potentials have other effects on the system. And the equation sheet states in small letters on the first page that unless we are told any differently, we always assume that the electric potential is measured relative to infinity. It says it right on the first page of the equation sheet. Capacitance is a bridge here. It's our manipulation of our system, which means we are now using the electric potential our knowledge of conductors and insulators to store energy. That's really what capacitance tends to be about. And our ability to store that energy and effectively measure how the energy is changed based on that storage. And then DC circuits, flow of charge, Ohm's law, and resistivity, Kirchhoff's laws. I'm going to spell it wrong because I'm about to be yeeted out. And then we have resistor circuits and RC circuits. Now we know our exam is going to be filled with these things, but there's going to be a focus. My expectation is we're probably going to see a 15-minute circuit question and, a larger electrostatics or capacitance question. I think that's, and it might be reversed, but I think that's really what we're going to see. Now look, we're out of time, and I want to have a moment here, but I want you to